The goal is to find the surface area of a twisted square prism as below. So the height is h, the square and the base has side length s, and we are twisting 90 degrees linearly with height. So that means the cross sections are squares that are rotating around the central blue line. So by symmetry, this is really just finding the surface area of this green surface S. Note that the green surface is not in any plane, so we actually have to use some Calc 3 to find it. So there's just this formula here that we are going to reference. The surface area of S is this double integral over R of the magnitude of the cross product of the u and v partials of R dA. So R is a parameterization where uv range through R. And the reason we might want to use a parameterization is because of how this is defined. So let's see exactly what this parameterization is. It turns out it's not obvious, but we'll figure it out. The first question is, how do we choose a coordinate system? So I've done it where the origin is here on the sort of the back left corner, but if you chose the origin at this base of the blue line here, that might make some things easier. That's just not what I did. So on the right, I have drawn a few coordinates in different colors. So in the purple here, these are the UV coordinates. And I suppose I didn't draw the XY coordinates, but you can see the yellow XYZ axis. Okay, so down here is UV equals 0, 0. And then as I increase U, I move this way to S0. If I'm at the top height, I'll move from U equals 0 to U equals S along the top. And as I move vertically with height, I'm increasing V. So in other words, V is just the height, but I suppose the coordinates of U are a little less clear in the XYZ coordinates, that is. So up here would be UV equals SH and UV equals 0H. Okay. So we can think of the region R as this collection of UV pairs. U is ranging between 0 and S, and V is ranging between 0 and H. So notice this is not sort of the region, like you could say in the XYZ plane underneath the surface, or the region of that bottom square. So it's clear that by definition V is just the height, which is Z. So the goal is to find X and Y in terms of U and V. Okay, so I've just recorded a table here with the points we know. The goal is, of course, then to find what these two are in general. So how can we do that? Here's what I did. Let's look at a top-down view of the surface. So sort of the black square is going to be the starting position of the rotating square, and then we're rotating by some angle theta to get the purple square. Now I'm thinking of this point here as fully arbitrary. So this is what we want to find the xy, notice we're in the xy plane of course, the xy coordinates of this UV point. So in green, here I've written the UV coordinates, and in black I've written the xy coordinates. So the goal is to find, I guess, the black coordinates for, or the xy coordinates for UV. Okay. So, on along here, again, what I'm doing is I'm starting at uv being 0, 0 and increasing u to s. Then once I've rotated a bit, I have some height, I guess v, and then u is still moving from this point to this point. You can think of this as rotating about this central point, which is in x, y coordinates, s over 2, s over 2. And the way we are rotating is just as you increase height, the angle changes linearly with height. That was our assumption. So you can think of this theta function as depending on uv is just a linear function of v. All right. So we want to figure out what a and b are in this case. So theta of u0, well, that's 0 by looking at this first point. And theta uh is pi over 2. So that means when this triangle has, this square is fully rotated, this point will have rotated 90 degrees to get all the way over here. And therefore, theta is just this precise linear function. Now some geometry. So I've copied the above picture, just labeled some of the vertices. So first note that we have a congruence of the two triangles ABC and DEC. Obviously, we're just rotating the same structure. Okay, but therefore the point of this is I just want to concretely verify that CB and CE have the same length, right, as we expect, and the angle ACB is the same as the angle DCE, so that in Cartesian coordinates, which is important to emphasize, and also in using the standard basis vectors to get our components, the vector CE, so let's use a different color, green, I guess. So this vector CE is a rotation matrix, rotating clockwise by angle theta, which you can think of as this matrix, times the vector CB, and these are thought of as column vectors, of course. So CB is one we started with. So you just rotate by angle theta, which is equivalent to just multiplying by this matrix. And therefore, if you start at the origin, go to C, you can get the vector the vector OE, so of course this is the vector OE, if you want, by just taking OC plus CE. CE is the rotation matrix for the angle, which is pi over 2h times v times this vector CB. And note that the vector CB, you have to subtract s over 2 in its coordinates. And so we simplify and we get this expression here. So now we have figured out what x and y are in terms of u and v. All right, next is a lot of algebra. So we'll just go through this very quickly, but you can compute the u and v partials. I've written them here. I just used some computer algebra system to do this. And then you can cross them and then take the magnitude and you get this expression here. This is one way to write it. I think there's certainly many other ways to write that. But anyway, now we go back to calculating the surface area. So we have to do this double integral. R is a nice rectangle, so we will just get constant terms in our bounds of integration. There's actually something to check here. I guess I didn't say that. But notice I went from a double to a single integral. So I did something. I basically canceled the h. Okay. And then, yeah, because notice there's only a u inside of here. Right? But then the question is to check that we do end up with a formula like this, where I've made these substitutions for simplicity. So maybe work through the integration here. So some questions, you know, what if I change the angle? What if I change the prism? For part 2, what if I fix rotating by 90 degrees, but see effectively what percentage increase I can get to if I just increase the height? And what about, I don't know, if you have a cross section like this? So let's just go through the integration. So we're starting here. Of course, we have some squares inside the square root, so we should use trigonometric substitution. Okay, so first you would use another substitution, so t equals 2u minus s. So this is preparing the integral, so bringing it to this form. And then we're going to use a trig substitution. So t equals 4h over pi tangent phi to bring it to the next form. And again, recall that arctan is an odd function when you work through this. So here, secant cubed, okay, how do you integrate secant cubed? Well, you would probably have to recall how this was done. It is usually done in a Calculus 2 course. But it's basically secant tangent times natural log secant plus tangent. Latter part in absolute value. So I think I have that as times 1/2. Yeah. So I say down here at the end that you should check the secant cube formula. Okay, regardless, let's just finish this off. So using this integration rule for secant cubed, we just plug everything in. And note that a lot of things simplify. So you're going to have to figure out what secant of arctan of something is. So secant arctan of x is just square root of 1 plus x squared. And in terms of our substitutions, this is very simple. This is just 1 over 4h times beta. And likewise, tan of arctan, well, there it completely cancels, so it's just going to be the inside, which is 1 over 4h alpha. Likewise, you can check the other computations in purple. Again, recall, you can pull these minus signs out. All right, then we get to the next step. So why can I take away the absolute values around the natural log? I will let you think about that. Meaning, what? In other words, why is the inside positive? And then, I guess I can do that. So I can simplify everything, and you get this expression. All right, so that finishes it off. Again, things to check are that trigonometric rule I mentioned, and also, you know, check this. What implication does that have in the following, or in the above argument? All right, thank you.